What do a freezing winter, artificial intelligence, and Bitcoin have in common? It sounds like the start of a strange joke, but the answer is actually shaping our future. They all consume absolutely massive amounts of energy, and together, they are quietly pushing global power demand in ways we're only just beginning to understand. Let's start with something we can all relate to: the weather. When a cold snap hits, what's the first thing you do? You crank up the heat. Now imagine that happening across an entire country, or even a whole continent. In many parts of the world, especially regions that rely heavily on natural gas and electricity for heating, a single colder than usual season can cause a massive spike in energy consumption. This isn't just about feeling cozy. It's about survival. But it puts an enormous strain on our energy grids, forcing them to deliver more power, more quickly, than on any average day. A cold winter isn't just a weather event, it's a massive energy event. And as climate patterns become more extreme, these energy spikes are becoming more frequent and more intense. Now, let's pivot from the physical world to the digital one. The digital world is expanding at a mind-boggling pace, and it's incredibly power-hungry. Think about everything you do online: streaming movies, scrolling through social media, joining a video call, or even just asking a smart assistant for the weather. All of that data lives somewhere, and that somewhere is a data center. Data centers are the invisible engines of our modern lives. They are massive, warehouse-sized buildings filled with thousands upon thousands of powerful computers or servers that store, process, and move data around the clock. They are the backbone of cloud computing, AI systems, streaming platforms, and yes, cryptocurrencies. Unlike your home, which uses energy in peaks and troughs throughout the day, these facilities operate at full tilt, 24 hours a day, 7 days a week, 365 days a year. They never sleep. And all those servers generate an immense amount of heat. So, not only do data centers need electricity to run the computers, they need even more electricity to run massive cooling systems to prevent them from overheating. We're talking about air conditioning on a colossal scale. The energy consumption is staggering. A single large data center can consume as much electricity as a small city. And we're not just building one or two of these. We're building them all over the world. The International Energy Agency reports that data centers, cryptocurrencies, and AI already account for about 2% of global electricity consumption. And that number is set to explode. Projections suggest that by 2026, the electricity demand from just these sectors could double. Let's zoom in on AI, the new kid on the block with an insatiable appetite for power. Training a single large AI model, like the ones behind advanced chatbots or image generators, can consume as much electricity as 100 households use in an entire year. And that's just for the training. Every time you ask that AI a question or give it a command, it uses more energy. As we integrate AI into more and more aspects of our lives, from business analytics to personal assistance, its energy footprint is going to grow exponentially. Then there's cryptocurrency. The process of mining currencies like Bitcoin involves solving incredibly complex mathematical problems. This requires immense computational power, which, you guessed it, consumes a vast amount of electricity. The entire Bitcoin network, for example, is estimated to use more electricity annually than entire countries like Argentina or the Netherlands. So, we have these three powerful forces all pushing energy demand upwards: extreme weather events, the explosive growth of data centers for our digital lives, and the rise of power-hungry technologies like AI and crypto. What happens when these demands collide? Imagine a freezing cold winter day. Everyone is at home with their heating on full blast. At the same time, millions are working from home, streaming content, and using cloud services. And in the background, our models are being trained and cryptocurrency is being mined. All of these demands hit the energy grid at the exact same moment. This is the new reality for grid operators. They have to perform a high-wire balancing act every single day. When demand spikes, they need to react in an instant to prevent blackouts. How do they do it? They rely on a complex and often fragile mix of energy sources. First, there are the renewables, solar and wind. These are fantastic. They're clean and their costs have been plummeting. We're building more solar and wind farms than ever before, and they are a critical part of our energy future. But they have a fundamental challenge: intermittency. The sun doesn't always shine, and the wind doesn't always blow. So, on a calm, cloudy winter day, solar and wind power might not be able to meet that peak demand on their own. This is where the second part of the mix comes in: dispatchable power. These are sources that can be turned on and off on command. The most common one today is natural gas. Natural gas power plants can ramp up production very quickly to fill the gaps left by renewables. They provide the reliability and flexibility the grid needs to handle sudden surges in demand. However, they are still fossil fuels and they produce carbon emissions. Then there's the third category, the backups. In many places, older, often less efficient power systems, like coal plants, are kept on standby. They might only be fired up a few days a year during extreme demand events, but they act as a crucial insurance policy against widespread outages. The challenge is balancing these three things: reliability, cost, and environmental impact. Everyone wants the lights to stay on, everyone wants affordable electricity, and everyone wants a cleaner planet. But right now, achieving all three at the same time, especially when demand is growing faster than we can upgrade our infrastructure, is incredibly difficult. We are in a complex transition period where the old and new energy systems are forced to coexist, sometimes uncomfortably. This isn't a problem for just one country. This is a global story. As developing nations digitize their economies, as AI becomes a standard business tool worldwide, and as climate variability affects every corner of the globe, the global appetite for energy is only going to increase. So, what's the path forward? It's not about stopping technological progress. AI and digital services offer incredible benefits to society. The question isn't whether technology will continue to grow, but how we adapt our energy systems to power it sustainably. The solution will likely involve a multi-pronged approach. We need to accelerate the deployment of renewables even faster. We need major investments in energy storage, like massive batteries, that can save solar and wind power for when it's needed most, smoothing out the intermittency problem. We need to build smarter, more resilient, and more efficient grids that can better manage fluctuating supply and demand. And we also need to get serious about energy efficiency. This includes making data centers themselves more efficient, finding innovative ways to cool them, and even locating them in colder climates to reduce cooling costs. The quiet collision of cold weather and powerful new technologies is forcing us to confront some of the biggest questions of our time. How do we power the 21st century? How do we build a future that is both technologically advanced and environmentally sustainable? There are no easy answers, but understanding the forces at play is the first critical step. The next time you turn up your thermostat on a chilly day or ask an AI to write a poem, remember the invisible, complex, and power-hungry system working behind the scenes to make it all possible. Thanks so much for watching. If you found this topic interesting, be sure to like this video and subscribe to the channel for more deep dives into the forces shaping our world. See you in the next one.